what this means, okay? So we have so this is time. This is temperature. Okay. And dependent on the size of the material we have, this is the cooling path. This is just an example, okay? So you step down, right? So on and so forth, until we reach room temperature. Okay. If you were to use, for example, if you are going to use a temperature, okay, over here, for example, this is like 350 degrees for stress relief anneal. Okay. And this you only need to spend for example, 2 hours. Right? For example. And every one of these stage over here, all these are 2 hours. 2, 4, 6, 8, 10, 12, 14, 16 hours. Okay. So when you do that at 350, right, you need to spend 2, 4, 6, 8, 10, 12, 14. 14 hours for what? Cooling. For control cooling. However, okay, if you do stress relief anneal at 250 degrees C, stress relief anneal, for now, because you use a lower temperature, you need what? Longer time, right? So for example, this takes what? 4 hours. However, the cooling become what? 2, 4, 6, 8. 8 hours of what? Can you see the consequences? Yes or no? Right? The higher the temperature you use, the less time is it for you to get rid of the stress, but more time is required for what? Control cooling. If you take lower temperature, it takes more time. Then after that, you do what? Control cooling. Clear? Okay. Now, this is just an example. The only way to get this is based on your component size, and you have to do experiment. Are we clear? I'm not saying that this is a fact, but you have to remember, the higher the temperature you take, okay, the longer you what? The shorter time is the relief temperature, but the longer time is the what? Cooling. The lower temperature you take, the longer time is the what? The relief temperature, but the shorter time is your what? Cooling. So there is a what? There's a mixed balance on this. Are we clear? Okay, so that is for our process or our stress relief anneal. And as you can see on this graph, right? That's why I say that the line can either go up or down, okay? Depend on what you choose. And you can use for any percentage of what? carbon. Okay. Now the next topic that I'm going to talk about, okay, as you can see earlier, okay, is what we call residual stresses. Okay. Now I'm going to do you a favor. Wait, let me think. Okay. Will not be tested in term tests. Okay. So whatever I wrote before, be tested. Residual stress will not be tested, but will appear in the what? Final exam. Okay. Right. So residual stresses are stresses that are locked into the material as a result of both mechanical and thermal loading induced by manufacturing processes. Okay. So there are two types of residual stresses. Okay. So one is what we call tensile, and tensile is usually usually what we call it our positive, and it's what we classify as unwanted. This is the first time something is positive, is unwanted. It's different from your bank account. And the second one too is what we call compressive. Compressive is the negative part, and it's what we want. Okay, the wanted one. Okay, so weird. Okay. And you will see later on why. Okay. So let's talk about the tensile, okay, residual stresses. Okay. So is the positive one, and we call it the unwanted ones. So micro cracks are usually generated in most manufacturing processes. Okay. So if we have a material, as I said, you're bound to have micro cracks. So at this stage, the applied stress is equal to what? Is 0. Okay. And if you were to ask me in terms of scale, roughly, this distance over here is about 5 micron meter. Okay, so if you see that length, that is 5 micrometer. A human hair is about what? 100 to 150 micrometer, depending on which part of the body. We clear? Okay. So in tensile residual stresses, it looks like this. The longer the arrow means the higher the value. Okay. So I would say longer the arrow, higher the residual stresses. Now this is without loading. Okay. And at this part, this is known as the crack tip. Okay. That's what? That's the crack tip. So with tensile, so what will happen if your stresses are like this? Does the crack want to grow or don't want to grow? You're pulling things apart, yes or no? It wants to grow, yes or no? So the tensile residual stress okay, it will promote okay, crack growth. Okay, it will promote crack growth. So tensile residual stresses are usually generated due to rapid heating and cooling, okay, due to rapid heating and cooling. Okay, so there is tensile residual stresses. Okay, so basically, rapid means it's under what? Thermal loading. Okay. Now, the next one is what we call compressive residual stresses. Okay. As I mentioned before, is the negative part and is the wanted part. You want this. Okay, no, you don't. So in compressive residual stress, so same diagram, we have a crack tip, right? So what happened here is the compressive stress, will want to push this inwards. And this is a good thing. Now, same thing, the applied stress is 0. So compressive residual stress, and if you have a crack tip,